Hello, my name is Matt, and this is our Layout and Quality Assurance with Robotic Total Stations course. You will see a number of benefits using Robotic Total Stations in your layout and quality assurance programs. You will immediately see the productivity gains. You'll see improved quality, communication between the office and field, and client handover. Anything with risk should be met with an appropriate level of control. There are multiple uses of your Robotic Total Station throughout the construction project lifecycle. At the top level, here's a way to think about the layout and inspection process in 4 steps. After you have completed this course, you have a strong understanding of the process of using Robotic Total Stations as part of your layout and quality assurance efforts. So, without further delay, let's get started. Hello, my name is Matt, and this is our Layout and Quality Assurance with Robotic Total Stations course. One of 4 courses are part of the In the Field Contech Academy curriculum for main contractors. In this course, we're going to look at how you can leverage Robotic Total Stations to improve your existing layout and quality assurance programs. My British colleagues may sometimes refer to layout as setting out. We have developed this course in partnership with a group of thought-leading construction professionals and trade associations so that you have the opportunity to benefit from their knowledge, experience, and lessons learned. From time to time, you'll also hear from my British Contech Academy partner. After you have completed this course, you have a strong understanding of the process of using Robotic Total Stations as part of your layout and quality assurance efforts. You will be armed with a set of very practical next steps to incorporating this technology on your project. This course was built primarily for main contractor project team members who spend the majority of their time out in the field. But it's also relevant to any foremen, surveyors, or site personnel responsible for laying out work or performing quality assurance verification of the placement of specific work. Very intentionally, in this course, we will not cover the use of any specific hardware or software. Our goal is to focus on the process. Following this course, if you'd like to learn more about potential solutions, we will provide links to best-in-class industry tools that will assist you and your team. To get started, we're going to take a look at why Robotic Total Stations are a relevant topic today and discuss the potential benefits for you and your project team. We'll then give an introduction to Robotic Total Stations so everyone has a base knowledge. To stay consistent with the rest of the courses in the Field curriculum, we will use the Perry model to structure the rest of the course. First, we will discuss how to plan for the use of Robotic Total Stations in your layout and quality assurance workflows. We'll then take a more detailed look at how you'll execute before we can discuss how you can leverage the digital data collected to report on project and program performance. As we do with all of our courses, we'll finish by looking at how you can ensure a process of continual improvement. You now have access to a set of free downloadable resources. You can download them by clicking on the Resources tab below. These resources may include templates, guides, supplementary materials, or starter kits, and they were provided to you by the Autodesk Contech Academy industry thought-leading partners, who helped us build these courses. Visit the Partners page to learn more about our partners and reach out if you would like to also help and give back to the construction industry by sharing your experiences. So, without further delay, let's get started. In this chapter, we'll first look at why the use of robotics, and Robotic Total Stations in particular, are relevant in construction today. We'll then discuss the opportunity and potential benefits of incorporating its use in your layout and quality assurance point verification programs. So why is this a relevant topic? Well, many years ago, the U.S. Department of Labor provided data that showed labor productivity over time broken out by industry. The findings were clear. While the trend of labor productivity increased year over year for all other non-farming industries, the productivity of the construction industry was stagnant. More recently, McKinsey & Company, one of the world's top management consulting firms, conducted research on the construction industry and reported similar findings in both the United Kingdom and Germany, demonstrating that this was a global challenge. There are a number of factors contributing to this challenge. According to a thought-leading construction firm from the Americas, One of the factors is that buildings are getting more complex. You rarely to never build the same thing twice, so you're always working on a custom project. Even if you were to build the same structure, the site is different, conditions are different, there's always something different. One of the industries with the most positive productivity gains over time has been manufacturing. They conversely will often produce the same product over and over again from a controlled environment. Construction has recently begun adopting a number of techniques from manufacturing with the emergence of lean practices, prefabrication techniques, and modular construction. The other big trend we see is the increased use of robotics in construction. The idea being that if we can automate a task with robotics, we can not only address this productivity challenge, but also improve safety and quality. Here are some uses of robotics we see in construction today. Unmanned vehicles like trucks and drones, coupled with machine guidance, are being used to not only deliver materials, but also to perform precision earthwork. Special purpose robots are being used for demolition, welding, cutting, drilling, affixing, and even bricklaying. This allows tradesmen like masons to focus on quality, safety, and machine tooling, while the robots do the heavy lifting. Some uses of robotics are being used to help improve our own physical capabilities. For example, there are exoskeleton suits that help support the weight of heavy tools. 3D printing technology with robotics that can print nearly any shape you could draw largely defray the traditional cost of creating custom parts. These robots are becoming more sophisticated in the materials that they can print and how easily they're tied to design and automation software. In 2015, Autodesk was part of a partnership that 3D printed an intricate steel bridge. Instead of trying to address all of these types of robots, who are very relevant in construction today, we're going to narrow down our focus for this course and talk specifically about robotic total stations. You will see a number of benefits using robotic total stations in your layout and quality assurance programs. You will immediately see the productivity gains we discussed earlier, but in addition, you'll see improved quality, communication between the office and field, and client handover. You'll find productivity gains both in performing layout of work, but also in the speed of performing quality checks. Any given day, a team of 2 with tape measure and string might average layout or verification of 200 points. With a total station, that same team will average 400 points. With a fully robotic total station, you only need a team of 1, and you're able to lay out an average of 600 points per day. That's nearly 600% more productive. What is interesting about this is what we decide to do with the time that's saved. One side benefit of going from a 2-person to a 1-person system is that the reduced crew size and time on site leads to decreased risk and improved safety. Resultantly, you'll see improved quality, both through the increased accuracy and additional quality checks you're able to perform with the time saved from improved productivity. Your quality checks will have improved accuracy through the precision measurement of your robotic total station. This precision depends on the way in which you are marking or validating a point, how far away the point is from the robotic total station, and of course, the specifications of your robotic total station. As a rule of thumb, you can get within 1/8 inch, just over 3 millimeters, of accuracy from 2,000 feet out, using a prism and pole. And if you just shoot a laser and are prismless, you can get within 1/8 inch from 1,000 feet out. Of course, if you are at closer range, you'll get increased accuracy. Since you're more productive with a robotic total station, you can increase the number of points being validated, increasing the probability that you catch something out of conformance and decreasing the risk that something was missed. On a recent high-rise condo project, a team was using their robotic total station to quality assure curtain wall embeds. There were 320 embeds per floor and 16 floors, totaling over 5,000 embeds to check. Without a robotic total station, they would have verified a sampling of them. But in the same time, with their robotic total station, they were able to check each and every one. Turns out they found 3 misplaced sleeves that required rework, which cost a couple $100 per sleeve. If they hadn't caught them before pouring the concrete, later in the project, they'd have had to scan the post-tension deck for cable first, and then core drill to resolve the issues, costing the project thousands per sleeve on top of the scheduling delays and headaches. Your layout and quality assurance procedures with a Robotic Total Station tighten both the efficiency and communication between your team working in the job office and your team out in the field. The team in the field has improved access to the most up-to-date design information without having to run back and forth to Job Trailer, and the team in the office has a better understanding of the real-world conditions and construction progress. One of the Contech Academy partners from the United Kingdom defines work completion in their quality assurance program as only once work has been verified. They don't pay for work installed. They only pay for work that has been verified. They have a tight tie between the field verification back to the job office schedule and consequently payroll system. They set up site control and provide their subcontractors access. Then they have their trades use Robotic Total Stations to document the location and effectively completion of their work. Additionally, you're able to improve the value of your handover. By leveraging the as-constructed information, you can find discrepancies and improve your design information to represent as built rather than as designed. As you can see, there are many benefits to using Robotic Total Stations on your projects. When one of the Contech Academy partners was first piloting a Robotic Total Station solution, they were working on a project in Hawaii where they were self-performing precast for a parking structure on an educational project. Each of the precast components had a dowel grouted into the sleeve, so that these panels, which were being prefabricated off-site, could arrive and get plugged in. With 875,000 dowels on the project, based on prior experience, they built in some contingency for a percentage of the dowels being off with natural error, and expected they'd have to rework them by chipping away at the grout, repositioning, and then re-epoxying them so the prefabricated panels would fit. Well, using the Robotic Total Station to position the dowels, not a single one had to be reworked. All panels were assembled without delay as soon as they arrived on site, and they completed that body of work 2 weeks ahead of schedule. Not only did they not incur the cost of reworking the dowels, but they had a number of benefits from completing the work 2 weeks quicker, including the crane rental that was hoisting the panels. Counting the cost of the Robotic Total Station, which they had rented for the project, the software they purchased, and training for their team using the tool for the first time, the project manager reported back to the business that they had over 10 times return on their investment. And this was their first project using it, so they had a bit of a learning curve. You can see in this example the productivity gains, as well as improved quality and reduced risk. What is even more interesting is that this new technique has changed what future bids have looked like, having adjusted their fee strategy. In this chapter, we've now covered why Robotic Total Stations are relevant in construction, and given some examples of benefits you might receive from its use. In this chapter, we'll give an overview of Robotic Total Stations. We'll discuss some of the basic components, how they're used at different points in the project lifecycle, and then talk about picking the right tool for the right job. Robotic Total Stations vary from a classic total station in that they allow the operator to control the instrument remotely, eliminating the need for a second teammate. The Robotic Total Station will sit on top of a tripod, traditionally positioned over a known point, commonly referred to as your control point. Establishing control on the site is one of the most important topics we'll cover in the coming chapters. The Robotic Total Station and tripod are stationary, but the Robotic Total Station will rotate around and look up and down to find the point you're verifying or laying out. The surveyor, foreman, or perhaps site manager will carry around a prism pole. Affixed to the top of the prism pole is the prism. This is what the Robotic Total Station looks for and can follow around by locking onto it with a laser beam. Once the Robotic Total Station is locked on the prism, when you move the prism, the Robotic Total Station will follow it. When laying out or quality checking the location of a point, the operator will use the data or field controller to help them navigate, position the bottom of the pole on the point, and then place a marker if laying out, or capture the actual real-world coordinates of the point if performing a QA check. Both the Robotic Total Station and the prism rod will have leveling bubbles on them for aid. The Robotic Total Station shoots a laser at the prism and uses that to keep track of where it moves. And the data and field controller on the Prism pole and the Robotic Total Station will send data to one another. Instead of covering it in this course, we've added a guide to the attached course resources that covers how to set up your total station. Additionally, I'll note that setup procedures may vary slightly from one hardware unit or vendor to another. I recommend you leverage your vendor to help you get set up the first time you use a Robotic Total Station. There are multiple uses of your Robotic Total Station throughout the construction project lifecycle. During feasibility, design, and planning, you want to survey and document existing site conditions for analysis. This may be for basics like understanding boundaries, setbacks, and easements, or for understanding existing conditions for design and planning purposes like understanding your grade. Before particular bodies of work are performed, you may use your Robotic Total Station to locate and mark control points from which further measurements are referenced. You'll then want to mark off where the work should occur, and so you'll use it to lay out, also referred to as setting out or staking out. Well before you pour your concrete pad, you need to set up formwork so your trades can come place rebar and rough in. You or your subcontractor may use your Robotic Total Station to mark off where formwork is set up, or perhaps where embeds or sleeves should be positioned. After work has been performed, you'll use your Robotic Total Station to validate that it's placed in the correct spot. Before you go and pour the concrete, but after your trades have come in and put in place all their work, you must double check the formwork is properly set up or hasn't been disturbed, especially if you have an irregular shape with an arc or angles. And you'll validate or quality assure the actual placement of the embeds and sleeves. After the concrete is poured, you can use your Robotic Total Station to perform a surface analysis on the slab to make sure there's no slumping. At handover, you can improve your client deliverable. Leveraging actual conditions captured, the design documents can be updated for accuracy to reflect as-built conditions with regard to placement of utilities or assets, for example. It's important that you pick the right tool for the job. Now that we've covered some example uses of your Robotic Total Station over the course of the project lifecycle, think about what your project team or teams will be using the machine for. There are a number of factors to consider when comparing Robotic Total Stations. Here are some you should think about with regard to your particular use. Two of the most obvious are range and accuracy. Range speaks to how far away the Robotic Total Station can validate points with the level of accuracy you require. You should think about what the average and maximum distance between your known control point and the points that you are laying out or validating, and what level of precision accuracy you'll need. Sensor stability is an important topic, but it isn't always thought of. You want to get set up, have the Robotic Total Station find your prism, and then get on with your work without interruption. Well, in the real-world practice, there are going to be some disruptions. Maybe someone walks between you and the Robotic Total Station, or you have to walk around a column and you lose what is referred to as lock on your prism. And so you have to reacquire it, which takes time and disrupts your work. Some Robotic Total Stations manage this better than others. The time it takes the robot to find your prism, also known as time to acquisition, determines how quickly you can recover from an interruption. Battery life of your Robotic Total Station should be considered. Carrying around a couple extra heavy-duty batteries so you can get a day's worth of work done in the field without coming back into the project office is a hassle. Basic ease of setup of the entire unit, including both the hardware and the software, is a factor. The hardware for setup of the unit, and software for its ease of getting the design information and point verification data to and from the robot is important. Most software tools have a basic level of compatibility with all the major hardware vendors through basic information exchange, but more detailed access to the design information for reference is very helpful to your field team. Some systems will only give your field team basic grid and column lines. Others will leverage 2D design information, and the best systems will give you access to 3D design information. The communication range, or distance and accessibility of design and point information, is important. Some Robotic Total Stations require reliable access to Wi-Fi, which is not always feasible. Other systems might rely on Bluetooth communication. You'll find that if you can get a reliable Wi-Fi signal, you'll have more responsive navigation. Finally, as with any tools, you of course want to consider price, warranty, and support. One size certainly does not fit all here. You need to understand what your job is before you can pick the right tool. In this chapter, we gave an overview of robotic total stations. We talked about some of the components that make it up. We talked about its use across the project lifecycle. And we talked about how to pick the right tool for the job. Armed with some basic information about robotic total stations, let's talk about what you need to plan for when performing layout and point verification or quality assurance activities. You'll want to determine what points need to be laid out or verified, understand how to establish control, and ensure alignment among stakeholders. First things first, you have to plan out what you're going to use your robotic total station for. You need to know where you're going to set control points so that your design team has time to incorporate those points into their design documentation. If they know about which points will commonly be validated ahead of time, they can embed them into their design tool families, so they're always there automatically. Talking about this with the quality director from one of the partners who helped build Contact Academy, he says, anything with risk should be met with an appropriate level of control. You can't possibly check the location of every part of every component on the project. So instead, you have to think about where your risk is. That is, which areas of work, if not located correctly, will have negative impacts on the project down the line. As a starting point, some very commonly laid out and verified points are anchor bolts, embeds, edge of slab and footings, wall studs, hangers, piping sleeves, stub ups, or any penetration points. Once you've decided what is worth checking, you want to be realistic about where you'll check them. For example, you may agree that you will validate the top center of an embed plate, or the center of the track for drywall studs. Traditionally, sleeves and embeds are almost always verified, since they are so important, but other things may be less important or span a large area, so you will want to pick some sample points. For example, you may only shoot 5, 10, or 15 points along a run of utilities. Developing more formal guidelines for deciding what points will be laid out and what points will be quality assured verified on a particular project will help you keep your team on the same page and create a baseline standard for quality. Often, the design and quality teams will work together early in the project to set some basic standards of types of components that require points so that the design team can easily incorporate them. One of the Contact Academy partners defined what is checked when putting together their project's BIM execution plan. So the BIM team knows what points need to be modeled. They sit down with the project site manager, quality manager, and sometimes bring in the foreman if they're self-performing work. They start talking about risk areas, and then it gets captured what their quality assurance measures are right in the plan. Then, as the project team moves to execution phase and work begins, every project is unique and things are going to happen. There'll be changes or perhaps particular trades start having a hard time, and your original plan may need to account for these factors. During the team's regular look-ahead and planning meetings, they should be talking about quality, and as part of this conversation, they should be identifying areas of risk and determining how that risk is met with an appropriate level of control. By thinking about what will cost the most in terms of dollars and downtime if it needs to be moved later on, you can easily see quality assuring your sleeves may cost you an hour, but if concrete is poured, it'll cost you $20,000 to drill out and move that sleeve, plus the downtime of a day or two.
Hi, my name is Dave, and I'm here to bring you my top tips on using robotic total stations for successful layout and quality assurance programs. Control can be established many different ways, but the goal is always the same: accuracy. Establishing accurate control and getting everyone working off the same control is necessary for a successful layout and point verification program. What is control? Well, at its most basic, the definition of control is the matching of points in the design documentation to those in the field or real world. Sounds simple, right? Remember that there are different types of survey and building controls in the industry. In most cases, the initial data will be a survey benchmark from a surveyor or an offset from a building grid line. Here are 3 points to keep in mind as you prepare to match control in your design information to control in the field. 1. The main contractor may provide surveyor control points or offsets from the grid through a list of coordinates. Most often, they're provided in some sort of offset from the structure or the survey benchmark locations for the site. 2. If the site has no control, you can make your own by laying out temporary benchmarks and offset points from the structure and matching them to your design information. For example, a 1200 mm square, that is 4 by 4 foot offset from columns A1, H1, A10 and H10 can be laid out and marked in the field for use. Then use these same offsets in your design documentation. 3. Verify your design points with field reality. If your design says the control point at H1 is 60 meters or 200 feet from control point H10, check that measurement in the field for deviations. If the design information says that between control points A1, A10 and H1 there is a 90-degree angle, make sure that's the case in the field. Angles are just as critical to accurate layout as the distance measurement. Establishing control on a job site is the act of physically checking all the control points necessary to continue your work. Never trust that control points are accurate until you have checked them yourself. When checking control, verify the error or deviation between the design file and the total station measurement. A deviation of 0 is optimal, but normal real-world conditions will leave us with about a 3 mm or 1/8 inch deviation. Deviations of 6 mm or 1/4 inch or more need to be verified and noted. Best practice is to check the distance between 2 points as well as the angular accuracy with respect to a third point. When your team is deciding where it will place control points, think about accessibility and longevity. For accessibility, think about where you will have points you are going to want to lay out and verify with consideration of line of sight. For longevity, it's best to establish control that will last. Every time you move control points, you're opening the door for error.
Successful layout and location validation, with or without a robotic total station, requires strong collaboration among stakeholders. The design team needs to be on the same page with one another, and then they need to ensure there is strong collaboration with the field team. For your design team, alignment starts with ensuring all design team stakeholders are working off the right coordinate system. They may leverage state plane, Universal Transverse Mercator, or UTM, or they could use a northing easting system. We won't cover this in detail in this course, but instead have added reference resources to help your design team. The design team also needs to ensure strong collaboration with your site personnel who are carrying out the work and the validation. This starts by working with their QA and site team to identify what points are worth laying out or validating so that they can ensure they're represented in the design documents. Constructability reviews are a great forum to have these types of conversations. Then, throughout the project, there should be regular bi-directional communication. The design team ensures the field team has access to the most up-to-date design documents at all times and is sure to highlight any changes, while the site team feeds back real-world conditions and raises issues for conversation when constructability and design are out of alignment. For your site team, just as important is alignment with their trades and subcontractors. They need to ensure the design information is communicated and there is clarity. Also, they need to ensure there is an expectation of level of quality and what controls should be in place. Often, the trades and subcontractors will be the ones using the Robotic Total Station for layout and their own quality assurance, so the main contractor will want to make sure that site and project control are properly established and accessible to them. In this chapter, we covered a number of the things you'll want to plan for heading into executing on your layout and verification processes with Robotic Total Station. We discussed how to determine what points need to be laid out or verified, establishing control, and ensuring alignment among stakeholders. In this chapter, we'll cover a 4-step approach to executing on your layout and inspection process. Then we'll discuss the first 3 of those steps in detail. First, how to create points in the design software. Second, transferring the design and point information to the Robotic Total Station. And third, some of the best practices for laying out or quality assure validating points. Both the process of laying out and the process of quality assurance validating points with your Robotic Total Station are the same. At the top level, here's a way to think about the layout and inspection process in 4 steps. Step 1, point creation. Your design team needs to represent or create the points in the design documentation. Step 2, transferring points. That information needs to get transferred to the Robotic Total Station in Data Collector. Step 3, capturing points. Your team needs to perform the actual layout or validation of those points. Step 4, analyzing point data. The actual real-world information about those points needs to be synchronized so that it can be analyzed and managed appropriately through reports. In this chapter, we'll cover how you execute a layout and inspection process with Robotic Total Station, focusing on the first 3 steps. Your design team needs to ensure that all points you want to lay out or validate are represented in the design documentation. This can be done in both 2D and 3D design information. You'll need to be involved in this process so that when you are out in the field working with this information, you understand what they are giving you to work with. Looking at the makeup of a point, there are some common attributes that you want to be familiar with and in sync on with your design team. First, make sure you have alignment on the coordinate system and format. Then, all points should be categorized properly. At a base level, there should be different representation of control points, points to layout, and points to quality assure. All points should have a unique identifier. Usually they are formatted with a prefix and then a number. For example, CP001 might represent control point number 1, and QA0034 might represent QA point number 34. Other teams may adopt a naming convention that helps describe the object being laid out or verified. For example, QA-SW-001 would be a quality assurance point of a shear wall number 1. 2 common prefixes are STK for a staked out point and AB for an as-built point. Another special type of point is an offset point, which is used when you can't safely access a particular point or it's easier to validate an offset. For example, you might have an elevator shaft and want to verify the opening, but there's a fence around the opening. So thinking ahead, the point is created as a 4-foot offset point from where the opening is to keep the team safe while QAing. Then, each point should have a property that designates the intended or design coordinates, and a separate place where the actual or real-world coordinates are captured. This is used to determine if there are any differences out of range of a particular tolerance. Optionally, each point might have information associated with it, like description or assignee, representing the person responsible for performing the layout or validation.
Many design software tools have add-ins to facilitate the rapid and accurate creation of points in your design documentation. Of course, points can be inserted manually, but they can also be created as an embedded part of pre-drawn components or model elements. This means that when such objects are added to the design, the points are embedded automatically. Further, you can create a large number of points all at once by creating a rule. For example, you could create a quality assurance point at the center of the opening for all sleeve objects greater than 200 millimeters or 8 inches in diameter in a design file.
Once points have been created, they need to be transferred out to the Robotic Total Station and Data Collector. you'll give it two sets of information. One is the points that have been created. The second set of information is the background design information, including information like scaling. Sometimes this design information is basic line work like grid lines. Other times, it's a 3D model. It should be noted that some hardware manufacturers' layout software can only handle certain file sizes and types. In the simplest form, all layout software, regardless of hardware manufacturer, pretty much universally will accept both the import and export of point information and the design information as CSV or TXT files. The lowest technical way this import and export occur is through a memory card. Most robotic total stations will accept at least 2D design information using DWG and DXF files. The easier and more common way information is passed in most modern machines is through some cloud-based solution that can synchronize. Most of the new robotic total stations will accept a 3D representation from a building information model so that you can better visualize where points are or should be. When passing in DXF, DWG, or building information models, be sure that you have set the scale properly, including setting unit of measured feet and inches or meters. There are instances where you'll be out in the field and you want to either back up the work you've done so far, call up the design team and ask them to add a couple other points that you believe should be staked out or verified, or there was a design change and you need to load up the latest information. In these situations, you won't have to run back to the project office if you have a cloud-based solution and your Robotic Total Station data controller has Wi-Fi or a cell modem. Now you're ready to get to work. When positioning your Robotic Total Station so you can lay out or verify points, there are two basic types of setup: known point setup and reference point setup. Known point setup is also referred to as occupy point setup, and is when you place your Robotic Total Station directly over top a known point, like a site control or project control point, so that it can orientate itself with relation to the design file. This is the most accurate and fastest way to set up your Robotic Total Station. The limitation, however, is when the distance between the points you need to verify and your control is too far away, or if there are line of sight issues. For example, if your project has a large elevator core in the middle of the building, and it's in between the points that you're trying to verify and your control point. When you have these line of sight issues, you can use reference point setup. This is sometimes called resection setup. Here you set up the Robotic Total Station anywhere up out of the way between your control point and the points you need to lay out, where you won't have line of sight issues. Since you aren't setting the Robotic Total Station up over a known location, it doesn't know where it is in space. So you have to help it out. You have to help it figure out what its coordinates are by shooting directly at a couple of control points, anywhere from 2 to 5. Once it knows where it is in relation to those control points, it can triangulate where it is in relationship to the design information that you gave it. One side benefit of this approach is that you can set the Robotic Total Station up out of the way in a safe location. Now, when performing layout or verification of points, here are 4 best practices to keep in mind. 1. Check your setup and the level of your total station every 40 shots or so. 2. Try to use the same control points each day. This will help to minimize the propagation of errors. 3. Do not shoot past your control setup. If the control points used are only 200 feet apart, you should not lay out or QA points past 200 feet from the total station. 4. Shoot long on control and work close to your total station. That is, you have the choice to use 2 control points that are 50 feet apart or 2 control points that are 200 feet apart. Use the set that's furthest apart. Then, when laying out or validating points, try to keep those points closer to your total station for greater accuracy. In this chapter, we discussed how to execute on your layout and inspection processes with Robotic Total Stations by covering in detail the first 3 steps of our 4-step process. We covered creating the points in the design software, transferring the design and point information to your Robotic Total Station, and then some best practices for you when laying out or validating your points. In the final step of our 4-step process, once real-world location information has been captured, we synchronize it back to our design tools, where we can perform analysis and take the appropriate action. In this chapter, we'll discuss a couple uses of this information and give examples of deviation reporting, surface analysis, and the use of project performance reporting with coverage and productivity analytics. With deviation reporting, you're looking for differences between the plan and the actual performance that might have an impact. We do this in 3 steps. First, get the as-built real-world point coordinates back to the design software. Second, for different types of points, determine what your tolerance is. Set a deviation threshold and perform the analysis, looking for discrepancies between the design coordinates and the actual coordinates. Most design software will automate this analysis for you. Finally, if a particular point or set of points is out of deviation, you have to decide what to do about it. Perhaps there needs to be a conversation, or some form of corrective action needs to be carried out. You should get this list of potential discrepancies from your design team and assign action items, ideally in the same centralized digital issue log you're using to track and ensure resolution to all other quality defects. You can reference our Quality Assurance in the Digital Age course for more details on this. Some examples of deviations might be that a sleeve was completely missing, or that hanger number 2 was too far in the project north direction and needs to be replaced. Sometimes this deviation report might be called a cut and fill report because it may tell your team when it needs to cut and fill. Another way to analyze actual real-world point location information is through surface analysis, like a slab or wall analysis. Similar to the deviation report, it's looking for differences between the design or plan location and the actual location of work. But it looks at this by taking samples on a surface. Here are 3 steps to performing this analysis. First, out in the field, you need to take a large sampling of actual points along the surface. Second, synchronize that information back to your digital design tools. Third, you're going to take a type of deviation report, but instead of setting one tolerance, you'll assign a color scheme to ranges of deviations, traditionally along one axis. And then you run the analysis. The output will be a visual depiction of the surface, colored, showing where you have deviations. If you perform this on a slab, for instance, you might find that there are areas you need to go in and grind the slab down to level. Or go back in and add a topping slab to fill in any low points. Two of the most basic ways you can use point layout and verification information is to analyze performance in terms of coverage and productivity. Coverage can be measured by counting the number of points verified or inspections performed in a particular area or on a particular body of work. We use this metric as an indicator of risk or exposure in our quality program. The idea being that the more points we have verified, the higher our coverage, and thus the lower the risk that there was a quality defect that we didn't spot. Another use of this information is to measure productivity of your team. As discussed at the beginning of the course, construction labor productivity is a global challenge. By benchmarking how many points or how long it takes to lay out a set of points without a robotic total station, we can then compare that with how long it takes with a robotic total station. This will help us to quantify the productivity value of the solution. This information is particularly relevant for teams piloting solutions and looking to report back to the larger business on the return on investment. In this chapter, we looked at some examples of how we use our point layout and verification information to identify non-conforming deviations in our deviation report and service analysis. Then we discussed how to measure and report on coverage and productivity. In this chapter, we will discuss how you can take the next steps in continuously improving your use of robotic total stations and technology on your job site. We'll first discuss how to include use of your robotic total station in your quality assurance program, working with your trades and subcontractors, setting up a site buddy system, and finally, ensuring ongoing training. As your use of robotic total stations evolves and more of your project team members become comfortable with the use and operation, we should start to think of the robotic total station as just another tool in our quality assurance program. We can treat point verification like any other quality inspection, where we ultimately want to work collaboratively with our trades and specialty contractors during regular quality meetings to discuss what points will be laid out or verified. For many teams, their look ahead, pull planning, or pre-task planning meetings are the best forum for these discussions. The closer we work with our trades and subcontractors, the better the project outcome. This applies to our quality program and use of robotic total stations as a tool in that program. To encourage your trades and subcontractors to participate, here are some tips. 1. Be clear about your expectations up front by including appropriate language in contracts that outlines how they will participate in the program. 2. Centralize and ensure that they have access to the latest up-to-date design information, as close to real-time as possible. 3. Take ownership of setting control on the site and for the project to make it easier for their field personnel to perform their own layout in QA point verification. As we discussed in our planning chapter, ensuring alignment among stakeholders is key to the success of your point layout and QA program. One of the keys was that there was strong collaboration between the design team and the field team. Take this opportunity to strengthen that relationship another step by setting up a job site buddy system, by pairing up a design team member, perhaps this is your BIM or VDC manager, with field personnel like your site manager or surveyor. In this relationship, encourage tag-along sessions. Encourage your field team to share their knowledge and experience of field and site conditions in the process behind performing layout or quality assurance verifications. Armed with a better understanding of the real-world challenges of your field team, like line of sight, will only improve the way your design team creates control points or offset points. On the other side, encourage your BIM or VDC managers to share their knowledge of the design world, including point creation and models. Finally, hardware will change on an annual basis. In order to facilitate continual improvement and keep up with the pace of change of technology, be sure to put in place a regular training program, whereby various topics are covered. Include new hardware training from subject matter experts as just one of these topics. Most times you can engage with your local hardware vendors to help facilitate this training. In this chapter, we discussed a couple ideas for ensuring a culture of continuous improvement. We talked about taking next steps in using a robotic total station as just another tool in your QA program, strengthening our relationship with our subcontractors, setting up a project buddy system, and facilitating ongoing training. Great job! At this point, you've completed the site layout and quality assurance with the Robotic Total Stations course and are ready to do the knowledge summary. Here you'll have 5 questions that will touch on a number of the important topics we have covered. Upon successful completion, we will generate and unlock your continuing professional development credit for download. After that, I encourage you to complete the remaining courses in the Field curriculum so that you can unlock the exam and become Contact Academy in the Field accredited, which you can include on your CV or resume, and even add as a badge to your LinkedIn profile. Also, don't forget to download and leverage the resources provided by the thought-leading partners who helped us create this course. Whether you're just getting started or have already begun using robotic total stations for layout and quality assurance, I hope this course helped provide you with some very practical ways you can improve your program starting tomorrow. So thanks again for joining me. Have a great day.